Good morning, all. I am privileged to present my research, which is titled Understanding Heat-Induced Stress in Portulacaria afra, that is used for restoration. It was a study that was conducted at Nelson Mandela University, and it was supervised under Professor Alistair J. Potts. Okay. So why is a study like this important, firstly? So starting off, Portulacaria afra, known as Spekboom, is a succulent native plant to South Africa in which we know it sequesters carbon as well as it is drought tolerant. It is also an ecosystem engineer in which it improves the quality of the soil as well as it promotes biodiversity. So it is also where with these traits, it is an important plant in entire restoration projects that are used in degraded landscapes. However, there was a study that was conducted last year around November-December in which it involved Spekboom cuttings, and the study found that there was a 90% mortality rate. The reason for this was unknown, and there were two objectives for this, which was either being air temperature extremes or soil temperature, elevated soil temperatures. So my entire study focuses on the elevated extreme temperatures. So why, again, is a study like this important? Well, the IPCC, or the Intergovernmental Panel of Climate Change, has predicted that there will be an increase in climate change of about 4.5 degrees Celsius by 2100. So what this means is essentially our heat waves will become more extreme. So for this, restoration efforts might be even more difficult if you don't understand how Spekboom handles this. So my entire study question was, how does a simulated heat wave affect Portulacaria afra's physiology? And to test this, we set out three objectives, which were to quantify the thermal tolerance limits, to assess the photosystem 2 integrity using photosynthesis integrity and photosynthesis efficiency, and then also we evaluated tissue-specific water mass content. So how this all happened was we had Spekboom cuttings that were provided by Nat Carbon Africa, and we had 4 trays. So in all 4 trays there were 10 cuttings that I used for the study. They were then divided into 2 control and 2 experimental trays. Thereafter, it was further subdivided into a watering and not watered group. How that essentially looked was, there's my little tray with one of the cuttings. You can see that the watered and not watered follow a diagonal pattern. And those are my grow chambers, which were a controlled and experimental grow chamber. Just as a little video, this is how they looked. Sorry for ripping the door open, but that's how they looked. So we also had the different temperatures. So for a 3-week period, we had an acclimation temperature. For a heat wave period, it was a week of about 24 to 45 degrees Celsius. And for a recovery period, it was just a week following the same temperatures as the acclimation period. We got this weather data from Gqeberha weather station, which was the main basis of our entire study, where we used the summer months here in the southern hemisphere. How my temperature data looked something like that. So as we can see, there is the acclimation period. Then around the heat, we can see the elevated temperatures for the experiment and the controlled state level. And then for the recovery, it followed the same patterns as that of the acclimation. For measurements, we did daily photosynthetic efficiency, which is the FV/FM ratio. Then we also did water mass content percentages in the leaves and the stems. And then further, we did some visual monitoring. So for the photosynthetic efficiency, we use something called a P, or a photosynthetic efficiency analyzer, which just shoots a little burst of light into a dark adapted leaf to be able to get the FV/FM ratio. We did some destructive sampling, which was where we removed the leaves from the stems and we cut the roots off. We weighed the samples, then we dried the samples, then we weighed them again. The drying was for a week at 80 degrees Celsius. Then we did some little visual monitoring. This was my first time working with any of this, which I was super happy about. So what we're going to be doing is we're going to start with visual monitoring. So this right here is a plant that was during the experimental phase of the heat treatment, which received no water at all. As we can see, there is some severe shriveling happening in the leaves as well as in the stem. However, this is the same plant at the recovery phase. So we can see that there is slight shriveling and the stem just looks more plump. Now, the recovery period is where there was a single watering that happened after the heat stress. Now, this is a plant again in the experimental phase where we can see he was watered, so his leaves are slightly shriveled, whereas his stem is not as shriveled. But when we go to him in the recovery phase after a single watering, we see that he is doing amazing. Now, for the photosynthetic efficiency analyzer, the values that we got and what we saw was any plant, the plants below 35 degrees Celsius, there was no impact whatsoever, with the FE over FM value being a 0.78. At 40 degrees, there was a slight decline in the photosynthetic efficiency, which is the FE over FM, at a 0.62. At 45, there was a severe decline, with the photosynthetic efficiency being at 0.55. However, after a single watering, that FV over FM bounced back to a 0.76. So for those that do not know what the photosynthetic efficiency is, or the FV over FM, if you are a plant and if you're at a 0.8, you are extremely happy. You are not stressed. If you're at a 0.6, you mid. You're okay, you mellow. If you're at a 0.4, you are severely stressed. So we can see here that the plant did so far start decreasing and increase up again. But how did that look? We get something like this. So before we continue, please note, the dotted lines represent the watering that I did. So watering was every Friday. And then the red rectangle represents the heat wave. So starting off at the non-water controlled section, we can see at day 4, there was already a decrease of photosynthetic efficiency, or the FE over FM. However, after the watering, it bounced back at where it immediately started following the starting. With the watered section in the control, there was no difference whatsoever. There was no decrease. It was stable. When we get to the non-watered experimental section, we see that again at day 4, photosynthetic efficiency started to decrease. However, after a single watering, it increased to its original photosynthetic efficiency. And lastly, here at the watered experimental, we can see that there are some fluctuations, but it is not as severe. Next, we did the water mass content with the destructive sampling. And what we saw was that watered plants had a higher water mass content, which is obvious. So the watered plants had an 83.6 water mass content, and the non-water plants had a 74.8% water mass content. Then we did it with the different tissues, which we actually saw that leaves contained more water compared to stems, with leaves being an 81.2% and the stem being 73.9%. But now how did this look? So here we all of a sudden got my little water mass content graph, where we can see that in the leaves, just to reiterate, the graph A is the water mass content after the heat wave, and B is the water mass content after the recovery. So in figure A, we can see that the plants that were watered, in the leaves of the plants that were watered, we can see that in the experimental, right over there, it has slightly less water than that of the control. However, if we go to the recovery, we see that it's all of a sudden similar, that is after one watering. If we go to the plants that are not watered, we can see that they have a lot less water mass content compared to that of the watered, but after the watering, they surpass the watered group. In the stems, we can see that they do hold less water than the leaves that was in the heat, but in the recovery, it stayed similar. So that means that the stems didn't lose or pick up any water. In the not watered section of the stem, we can see that the experimental had quite a decline in water mass content. However, it was fairly stable again when it was watered. So what does this all tell us? Well, from the study we could see that Portulacaria afra does tolerate 35 degrees Celsius and less. It is sensitive to the extremes, but however, after a single watering, it is able to bounce back and become its happy self again. Next, what we saw was that Portulacaria afra can go an extended period of time without water. My entire study was a 39-day period study, with it not having water for 31 days, which is essentially a month, as well as there was a heat wave as well. So this is how Spekboom is able to handle its drought tolerance through its different tissue levels, as well as, again, after a single watering, it takes all of the water up and it's able to survive. Further studies for this would be able to test whether the soil now has an impact, because as you could see, the air temperatures do not have much of an impact thereof. Nonetheless, I would like to thank Nat Carbon Africa for providing the funding as well as the Spekboom cuttings for this research. There's Prof. Alistair J. Podds for his mentorship as well as his time. There's Nelson Mandela University for its facilities. And lastly, the botany technicians for assisting me with equipment. Thank you.